Okay, hi everybody. Thanks for making it to this slightly different venue. I think it's really fine. So we have today a very special guest, Dan Stapleton, who's a friend of Kurn, friend of ours for ages and ages and ages. Just across the bay at that other institution. He got his PhD from MIT, in Wolfgang Photos Group, and then moved out that. And then he started his own independent research group at Berkeley, and he's been there for 24 years, I don't know, something like that. So Dan is a fellow of fellow of OSA. He's won every award you can possibly imagine. He is a winner of the Damon Thesis Prize. It's a wonderful thing. Like that. Sloan Fellow, Packard Fellow. He case, he was a case for the White House. And most recently, he won the Beats Prize. So, anyways, Dan is an expert in pretty much every aspect of AMO physics, from easy physics, exploring interesting interference, the foundational experiments with DC spinners, optomechanics, cavity QED. Everything in between, the lattice physics.
All right. Hey, thanks very much, Ben, for a nice and personal introduction. And thanks for everybody being here, not just now, but also the last day plus, seeing your labs, having lunch with a whole bunch of students. That's been really fun. It's nice that I've actually been to Stanford a fair bit recently. So we're hoping to interlace a lot of connections on the two sides of the bay, and I think we're succeeding in doing so. So I hope to see all of you up at Berkeley sometime soon. Just swing by, we'll host you, show you the labs, et cetera. I'll be happy to reciprocate. I'd like to, I gave a talk at the Crazy Cavity Workshop a few months ago. That was on our cavity QED experiment. So I thought upon this visit, maybe I should not talk about that topic and talk about the other things that are happening in my group. And I've sort of lumped them together in the title of this talk. So, so we're going to be focusing on quantum simulation, and in particular of things related to condensed matter physics. And this, is a certain flavor of the experimental work that we do in cold atom physics. So, by way of starting, I wanted to share with you a really exciting result that I actually read in Science. I picked up my issue of Science this week, and I read this amazing article about precision metallurgy. And they've measured the resistance of a bar of aluminum to a really high degree of precision. Okay, everybody's nodding, like, what the hell is he talking about? Because, of course, no one would ever do this, because solid state materials are messy. They're very irreproducible. They're full of defects and junk. Like you see this little, thumbprint on this image over here. And there's no reason in the world why you would want to make high precision measurements of this kind of solid state, because there's some resemblance of the solid state system to the model of solid state physics that would describe, let's say, electrons in aluminum, but there's not a very close match because it's a complicated, dirty material. That's not true across all of condensed matter physics. So there are certain systems, and I think of the carbon structures in particular as being examples where, actually it's one of these rare examples where the theory of condensed matter physics ends up matching very precisely to the actual experimental observations in condensed matter. So you can go and measure, let's say, optical absorption of a single sheet of graphene, and you can really try to compare it to a well-defined theory with many digits. So there are areas of condensed matter physics where condensed matter theory is actually the thing that's being precisely tested. But the cold atom realizations of the systems that look like condensed matter physics are sort of, I would regard as another place where we get to make real precise tests and probes and try to understand at a quantitative level every wrinkle and every number that comes out of condensed matter theories. And so the topic of quantum simulation you think of as maybe using a simulation to understand what actually happens in condensed matter. That's one way to think of it. The other way the other way I like to think about it is like atoms just make for interesting materials, and we're studying their material science is also a way to think about it. And of course, there's a lot of kind of landmark directions that have populated this field of quantum simulation for the last couple of decades. Studies of quantum fluids that I've been involved in, study of ultracold fermions, which I'm starting to get involved in, interesting new kinds of materials that, or systems where you can probe actually high dimensional physics in an experimental setting. I will talk about band structure in particular, sort of looking at the resemblances between optical lattice systems and materials. Some of my work is also kind of in the direction of mesoscopic physics. That's stuff that I talked about last time I was here. But anyhow, this is kind of the area in which I want to frame the topics of the next slides. And so I'll tell you about results coming out of 2 out of the 3 experimental setups in my group. One of them is an experimental setup where we place atoms in optical lattices. And our current focus is to understand impacts of the geometry of band structure on the properties of materials or many-body systems that occupy those lattices. And then I'll switch to a second topic, which is our efforts to laser cool a new family of atoms, transition metals, and sort of where we are on that path. All right, so let's start with that first topic, which is, let's say, studying systems that have band structure and then understanding what the consequences of that band structure is. So this, of course, is a central preoccupation of condensed matter physics, where one knows that specific properties of the band structure of materials have impact on the material properties themselves. So, for example, if I focus on 2-dimensional systems, which will be the most pertinent to what I'm going to tell you about, then we know that, for example, in things like graphene, there are some specific elements of band structure. Let's say points where bands touch one another, cross one another, and the specific nature of the states around those band touching end up influencing the bulk material properties. So, for example, current conduction in graphene will be affected by the geometry or the nature of states on either side of the Dirac point in graphene. And there's also quadratic band touching points and how they influence interesting effects. Finally, there's this beautiful observation that at a particular magic angle, graphene, two layers of graphene placed on one another have interesting interacting electron systems. And those come out from, there being kind of a magic angle at which you can create a band within the band structure that has almost no dispersion. So these are kind of a lot of phenomenology in condensed matter physics where some interesting features in band structure lead to some kind of material properties. So it's kind of a natural play space for us to think about in terms of cold atom physics, make some things like crystals that have these kinds of features, band touching points, the geometry around a band touching point, flat bands, and then see what the consequence is. So experimentally, the way we've done this in my lab now for some time is to work with 2-dimensional lattices. We're focusing on kind of 2-dimensional systems. And we built a system some years ago where atoms inside of vacuum are exposed to beams of light coming in three directions. The interference between these 3 beams creates sort of a triangular type of optical lattice. That's the interference of these laser beams. And another feature of our setup is that we use light of 2 different colors that have an exact 2-to-1 wavelength ratio. And we also control, through closed feedback control, the relative phases, or if you will, the frequency differences between the different beams that are forming these interference patterns. And with that, we're able to very sensitively control the position of the optical lattice that's formed as a function of time with like closed feedback control. And we've done a number of experiments over the years, first starting with rubidium atoms. That was the first thing we learned to place in these lattices. In the last few years, we've learned how to place potassium into the lattices, and that's allowing us to study Fermi gases and not just Bose gases. And with this kind of two-color lattice setup, we're able to project a number of different lattice geometries onto the atoms. So for example, if we just use the light that's at 532 nanometer wavelength, the interference of those three beams of light creates this intensity pattern that I'm representing here. And it's an intensity pattern where there's a triangular lattice of locations where the intensity goes to 0. And it turns out that with this light being blue detuned from an atomic transition, either rubidium or potassium atoms will be trapped at the dark sites in the optical lattice, and that would form a triangular lattice. So we can place atoms in here, and now they're in a two-dimensional triangular lattice. Alternately, we can use light at the longer wavelength, and the interference pattern is the same, just magnified by a factor of 2. But now, because the light is red detuned from atomic resonance, the atoms are attracted to the high-intensity spots of the lattice. And in this particular lattice, the high-intensity spots, they form a honeycomb lattice, like what you see in a sheet of graphene. And by overlaying these two lattices atop one another with a particular relative position of the two, we can also create what's known as the kagome lattice potential. So it's a lattice where there's triangular plaquettes that are joined at their vertices. And the kagome lattice is interesting because it shows the effects of geometric frustration. All right, so most of what I'm going to tell you about is actually going to be work that we've done in the honeycomb lattice, where we've tried to probe the geometric properties of its band structure. Okay, the honeycomb lattice has some interesting features in it. So here's the honeycomb lattice has, in 2 dimensions, has 2 s orbital bands. These come from the fact that the unit cell of the honeycomb lattice has 2 sites in it. And as you probably know, these 2 s orbital bands, they disperse, but they also touch one another because of symmetry at the k or the k prime points of the Brillouin zone. And at these locations, they have these linear band touching points where the energy of states varies linearly away from the degenerate spot. The graphene lattice also has excited states. So if I look at the p orbitals, there's 2 dimensions of motion in x and y, and there's 2 sites. So there's 4 pre-orbitals altogether. And these p orbitals, there's 1, 2, 3, 4 of them. They have some interesting properties also. They also have linear band touching points, let's say between the 1, 2, 3, 4th and 5th bands of the honeycomb lattice. And then there's also a quadratic band touching point where the energy varies quadratically in quasi-momentum away from that location between the 3rd and 4th bands. So the honeycomb lattice allows us to see a lot of these features that we knew were interesting from the study of graphene and bilayer graphene. So we decided to pay attention to that at first. All right, now all the interesting stuff in this lattice is away from the ground state. So in these experiments, we were working with a gas of bosons. The bosons, when we cool them down, they Bose condense in the lowest energy state of the lattice, which is at the gamma point in the first band. Nothing terribly interesting happening there. In order to look at the interesting stuff, we had to learn how to promote these bosons up to higher energy block states where some of these interesting features show up. And so we've learned how to do that. And the procedure is as follows. So let's say I take a gas of atoms. Again, these are bosons to start with. We cool them down in an optical lattice. And as I said, they form in the lowest energy state of the lattice, the ground band, and at the gamma point. But now what we do is we accelerate the lattice by putting on frequency differences between the beams that form the lattice, so that the lattice is now moving with some non-zero velocity. And in the frame of the lattice, this looks like we've applied a force to the atoms. And as you know, particles in a periodic potential, when they're subject to a force, they change their quasi-momentum, just like free particles change their momentum. And as such, this gas of atoms that is stationary in the lab frame is actually can be considered to be moving within the lattice frame at some non-zero quasi-momentum. And since we can control that quasi-momentum path by accelerating the lattice in different directions in this very controlled manner, we can take atoms on an excursion through band structure, through anything that is adiabatically coupled to the ground state. But now what about these excited states? There's also some physics in the excited bands that we wanted to access. So we've also learned how to place atoms into the excited bands. And what we do now is we adiabatically introduce atoms into a lattice that is moving. And so what happens now is as you adiabatically ramp up the lattice, the atom's state adiabatically evolves from in the lattice frame, from a momentum state, a momentum eigenstate, because they're moving at some fixed velocity with respect to the moving lattice, to a block state. And the adiabatic mapping between velocity states and block states accesses the high energy states in band structure. So for example, if I had initially accelerated atoms, or equivalently accelerated the lattice, so that the atoms are now in a state with a finite velocity that's, let's say, in the second Brillouin zone, then now when I adiabatically turn on the intensity of the lattice, the atoms will map onto the second band at that particular quasi-momentum. And now we can again move around in quasi-momentum through the methods I showed you earlier and move the atoms to different places, again in band structure. Okay, so that was our method with the bosons at least, and we used that to study the impact of band touching points on parallel transport. That was our focus. Okay, so in the graphene lattice, as I said earlier, there are these Dirac points at the K and K prime points of the Brillouin zone, where the bands vary linearly in energy as you move away from the degeneracy point. So the first band and the second band touch at that location. And this Dirac point not only has an interesting energy structure where the energy varies linearly as you move away, but it also has an interesting geometry. And what I mean by this geometry is that we can ask, how does the state on either of these bands, the lower band or upper band, how does it vary in its content and its definition as you move around in quasi-momentum? It's a little bit like asking on a surface that has a certain shape, how does, let's say, the tangent vector change as I move along the surface? Again, kind of a geometric characterization of surfaces. It turns out that the geometric structure at the Dirac point can be described by this picture. So in a certain basis, if I look at the block state wave function, the basis I'll choose actually is whether the atom is confined in site A or site B of the unit cell. In that basis, that two-state basis, the states around the Dirac point can be thought of as the states of a spin 1/2 particle in a sideways oriented magnetic field. And that direction of the magnetic field varies with the distance you are in quasi-momentum away from the Dirac point. That ends up describing the entire geometry around the Dirac point. Okay, so that's an interesting state geometry. So it means that as you move around the Dirac point, the orientation of the state changes, and that should remind you of things related to Berry phases, and that's exactly something that is a characteristic of the geometry around this Dirac point. Okay, so now we thought to ourselves, many of us have thought to ourselves experimentally, how do we experimentally characterize the geometric structure at this point? And in particular, the fact that there's really like a singularity in this geometric structure, right? Because as you approach the Dirac point from different directions, your state is really quite different, right? Along this direction, it's the state of a pseudomagnetic, the pseudo spin pointing sideways. Here it's the pseudo spin pointing, let's say, up in the plane, whatever. So there's a couple of ways in which people have approached it. So the first one is a great experiment that Monica also participated in while she was postdocing, is to measure the Berry phase. So you measure the Berry phase, this, as you expect, if you go around a circle, if you adiabatically, so through parallel transport, drag a state around the Dirac point, it should pick up an extra phase of pi, just like if you take a spin 1/2 particle and spin it around by 1 revolution. So that Berry phase is something that's measurable, and the way they measured it is through interferometry. So they took a gas of bosons, again, a Bose condensed gas. They placed the atoms in 2 different spin states, and then they used spin-dependent forces to push these atoms on a parallel transport trajectory through band structure. And the trajectory was such that the 2 pieces of the wave function went around the Dirac point, And then upon re-interfering the two pieces of the wave function, that is completing this kind of spin interferometer on the other side of the Dirac point, they could see jumps of pi in this interferometric phase whenever the path went around the Dirac point. So that characterized the Berry phase, that is, which is a characteristic of this singularity. In our experiments, we thought about a different approach, which is not to go around the singular point, but to go right into it. And so we considered a different parallel transport question. What happens, again, parallel transport, we're going to slowly transport the atoms on a trajectory. What happens if, let's say, we take our atoms, we start them in the lower band of this two-band system, away from the Dirac point, and then we slowly translate them right onto the singularity itself. And then on a path that remains continuous, but whose tangent is discontinuous, we leave along a path which is turned by some angle. And it turns out that as you do this, the atoms should undergo a rotation in the two-state space that touches at this band touching. So you do the calculation, you find out that the population, let's say in the lower band after this process, would go like cosine squared of the turning angle that differentiates the input and the output path. And the fact that this is a theta over 2 here in the expression and not a theta or a 3 theta over 2 is to say that characterizes the fact that there's one winding of this pseudo-magnetic field around the Dirac point. So it's the influence of band structure geometry, and in particular about singular points in that band structure geometry on the outcome of parallel transport. Okay, so we do the experiments, and the data are a little bit hard to explain, so I'll just flash them. But we take our atoms from their initial point, the gamma point in the ground band. We push them on a path exactly to the K point on the Brillouin zone, and then we push them at some angle away from that. And we characterize through a method known as band mapping. We project from band states back onto velocity states. We determine how many atoms are in the different bands of the lattice. And when we do so, as we change this turning angle, we see this sort of telltale cosine squared theta over 2 variation of the population, let's say, in the ground band, which is a way of experimentally characterizing the singularity at this Dirac point, or turned on its face, is a way in which the singularity at the Dirac point influences a material property, which is the outcome of a parallel transport. We can do the same thing at the quadratic band touching in the honeycomb lattice. So this makes use of what I mentioned earlier, which is that we can place the atoms in high energy bands of the lattice. So in this experiment, we started by placing atoms in the 3rd Brillouin zone, and then we pushed them toward the singular point at the gamma point and turned away from that singular point. And as a function of angle, now we see a cosine squared of theta variation, or we see 2 windings of this pseudo-magnetic field around the quadratic band touching point, which explains a little bit why it's quadratic and not linear. So we characterize that geometry as well. Okay, so now I use the word geometry a lot, so let me define what I meant. When I drew this picture and I showed you what is the nature of states around the Dirac point as a function of quasi-momentum, I was actually telling you sort of 3 things implicitly. One thing I was telling you is how the lower band states, there's 2 bands that touch here, I was telling you how those states vary as a function of quasi-momentum. I was telling you how the upper band states, so the lower band states, let's say they're the states of a pseudo-spin that points along the direction of this magnetic field. I told you how the upper band states vary with quasi-momentum, which is the opposite direction of the pseudo-spin. And then I also implicitly told you that there's a relation between the lower band and the upper band states. There's a relation between these 2 band structures, right? And that's how we could make a transition from one band structure onto another. So it turns out that the geometry of band structure can be quantified by all sorts of different quantities, all of which play interesting roles in the geometric theory of band structure. So maybe you've read papers about things called the quantum geometric tensor, which has a real part and an imaginary part. The real part is something that measures the distance between quantum states, and the other part measures sort of Berry curvature, or the a different projection of how states, a different way of characterizing how states vary on a surface. So for the next piece of the talk, I'd like to focus on one of these measures of geometry, which is something known as the Berry connection. So here's a definition of the Berry connection. It's a vector. You see there's a gradient here with respect to quasi-momentum, so that is a vector. It has the same, it's a vector that has dimensions of position. It's a matrix. It relates two bands to one another. So you've probably seen this before. So the diagonal Berry connection, that's the one that we often think about when we think about adiabatic processes in quantum mechanics, ends up describing the geometry of just a single state manifold, or in this case, a single band. So in that case, we're asking, let's say, how does the, if I look at the block state in one band as a function of quasi-momentum, and I take the gradient with respect to quasi-momentum, how much does that overlap with the state itself? That's kind of the standard Berry connection. If you take the curl of this, you get the Berry curvature. If you integrate up the Berry curvature, you get Chern numbers and Berry phases and stuff. So that's one of the things that we've seen a lot show up in the physics of condensed matter recently. There's also, this is a matrix though, so it also has off-diagonal components. And the off-diagonal Berry connection is saying something different. It's like the relative geometry between two surfaces, rather than specifying the geometry of each surface individually. And so it would be, let's say, I look at how the variation of the state in one band overlaps with states in the other band. That's the off-diagonal Berry connection. The diagonal Berry connections are answering these first two questions. They're telling us how the states of one band vary with quasi-momentum. And the off-diagonal Berry connection answers this third question, which is how transitions between one band to the other can occur. Okay, so what's the relevance? So here's my bird's eye view of condensed matter physics over the last 100 years. Since the first theoretical derivation of band structure by Bloch, we've had a band theory. Band theory is a theory that tells us what are the energies and what are the energy eigenstates of a particle in a translationally in a periodic system. And so what you get from the theory of band structure is some mathematical information. You learn about that there's bands, energy bands that have gaps between them. You learn about the dispersion, so how much the energy varies with momentum. You learn about the density of states and so forth. That's the information that band structure gives you, like in the mathematics. And then the physicists go and try to figure out, what do these math quantities mean in terms of things that I can actually see in a material and measure? And so band structure explains also all sorts of interesting observable things, like the fact that there's conductors, insulators, and semiconductors, the fact that superconductivity occurs and at what temperature it occurs. And so that's all properties of band structure itself. Now, since the roughly 1980s, a new awareness about band structure has emerged, which pays attention more to the geometric or the topological nature of bands related to what I just told you about. So in band geometry, we think about quantities like the Berry connection and so forth. We think about Chern numbers. We think about the existence of edge modes that must occur in the presence of a non-zero Chern number. There's new quantities that I'll talk about later as well. There's a whole sort of a book of mathematics related to the geometry and topology of bands. And then there's a bunch of us physicists who are just trying to figure out, what does this have to do with real stuff? How does it show up in an actual experiment? And there's a lot of things that people have focused on in the last few decades that come out as a consequence of the geometry and topology of bands. So what I want to tell you about next is an exploration in our lab of another one of these connections, which connects this mathematical quantity that I told you about in the previous slide, which is the relative geometry of two bands, and shows how it's related to another important concept, which is the optical response of materials. I mean, it's not a connection that we invented, but it's one that we're sort of evincing in our experiments. Okay. So here's something I've learned in the last few weeks. When you drive a transition in a material using light from one band to another, what's the strength of the transition? That's the question. Okay, so I'm an atomic physicist. First, I'm going to remind myself how that works for atoms. So if I have an atom and I drive it with light, I can ask questions about light-atom interactions. And to answer those questions, I have to know what are the states of the atom that we're going from and going to, let's say in an optical transition. And I have to measure matrix elements. In particular, I know that light interacts with matter largely through the dipole interaction, the electric dipole interaction. And it turns out that the relevant quantity for answering all the questions about light-atom interactions is subsumed by this matrix element, the matrix element of the position operator between two different states of an atom. And it gives me information about the strength of transitions. It also gives me information like if I have a state that's a superposition of two levels of the atom, I can ask what's its polarization, what's its electric dipole moment. So for example, if I have an S state and a P state and a superposition of them, I now can understand based on either drawing the wave function or just knowing what this quantity is, that for that particular combination, the polarization is such that there's more charge, let's say, on the right side than there is on the left. So there's positive polarization. How about in a material? Okay, so similar, we have light that comes in impingent on a crystalline solid. So one thing to realize about the interaction of light with materials is that the wavelength of light is typically huge compared to the lattice spacing inside the material. That's like the equivalent of the dipole approximation. So as far as the material is concerned, light is basically a uniform electric field that jiggles back and forth in time. This uniform electric field, because it doesn't have any momentum to it with respect to any substantial momentum, drives transitions from one band to the other that don't change the quasi-momentum. That's what light does in a material. Now, with what strength does it do that? Okay, so I can follow the same procedure as I had with atoms. Let's look at the block state, or the state within the unit cell for one band and for another band. And maybe all I have to do is evaluate like the same matrix element of the position operator between the ground band and the excited band of a transition. Okay, that's probably true. Or for example, if I want to know what is the polarization of a medium, like when you expose a medium to an electric field, if it's a dielectric, it acquires a polarization. That's like the density of dipole moments. So what is that? What is the polarization? So maybe I follow the same procedure. I have an initial state, which is maybe because of an electric field. There's an initial state, which is a superposition of different band states. So I look in the unit cell and I look, oh, behold, in the unit cell, I see more population on the right than I do on the left. So this would be a state that has a polarization in that direction. Maybe it's all the same as in an atom. But is it? Because who's to say what exactly is the shape of a unit cell in a material? Who gets to decide? I mean, anything that has a length A is a good unit cell. It doesn't have to be connected. It can be different pieces. And then who's to say that this particular superposition of these two bands has a polarization pointing in that direction? Because if I drew a different, remember, everything is spatially periodic. If I consider not this to be the unit cell in the crystal, but this to be the unit cell in the crystal, then lo and behold, the polarization actually points in that direction. So applying these ideas inside of a crystal is kind of weird. And we've known it's weird since roughly 2000, it turns out. And like a modern theory of polarization in materials has emerged. And one of the outcomes of that theory is that when you want to calculate the strength of an optical transition in a solid, you have to evaluate this quantity. Okay, lots of math, but that's the quantity that is relevant for measuring the optical response of materials. So let me bring that up. So for example, if we're talking about interband transitions, so I and J are different, this term here goes away, then the matrix element that governs the line strength for excitation in a solid is the off-diagonal Berry connection. That's what it is. And that's what physical consequence it has. And it also tells you that it's a measurable quantity. So if you're asking how strongly do you drive a transition from one band to another with a particular polarization of light, then the matrix element, or let's say at a Fermi golden rule kind of thing, the matrix element squared, is just measuring one projection of this off-diagonal Berry connection, is measuring its magnitude. So that's kind of cool. You might ask why this is true. I certainly did. So it turns out that it's just math. So math is correct. It turns out there's also a little bit of physics behind it. So again, an electric field, the electric field of light gives a uniform force on electrons that is modulated in time. So on the lower band, let's say, the electrons are moving back and forth in quasi-momentum as they're exposed to light. And then we can ask, how much does this jiggling back and forth in band structure couple to the upper band? You think it would probably have to do with how this variation overlaps with the band above. So that's kind of the explanation physics-wise. All right, now let me bring us back from condensed matter theory to atomic physics. And how do we do this in our experiments? So optical spectroscopy of materials is, after all, exposing materials to light, which is like this uniform applied force on the electrons. In our experiments, the equivalent is to take the crystal in which the atoms are held and jiggle it back and forth periodically, and then look at the response. So what we're going to be doing is lattice shaking spectroscopy. That's going to be my tool for simulating the optical response of materials. The equivalent of the optical polarization is, again, this should have been lattice, is the direction in which we shake the lattice. So we can look at one polarization of excitation or a different polarization, or we can drive the thing in circles to simulate how a material responds to circular polarized light. And if we can now measure the excitation rate at every quasi-momentum, which is something we can uniquely do in atomic physics, but is hard to do in materials because you just kind of measure the bulk electronic response, then we can now measure components of the interband Berry connection and characterize this quantity experimentally. All right, so to do these experiments, we started making use of our ultracold fermions in the lattice. So I won't go through a long song and dance about how we get them in there, but we take a mixture of rubidium and potassium atoms, we cool the two of them down together, we end up with spin polarized gases of the fermions that are at a temperature which is about 10% of the Fermi temperature, turns out. And we can vary the chemical potential of this Fermi gas by changing the number of atoms in the lattice. So here's data from the kagome lattice where we can keep filling the different band structure in the lower bands of the kagome lattice by changing the atom number. In this experiment, we're actually going to be focused on the honeycomb lattice, not the kagome lattice. All right, so the way the experiments are done are pretty simple. We're going to load atoms into the lattice, we're going to shake the lattice, then we're going to see how the atoms in the lattice respond. We're going to see so here's the modulation of the position of the lattice, and after we're done with that modulation, we characterize the population of atoms after this excitation by one of two measures. Either we just turn off the lattice and everything flies apart and we measure the velocity distribution. That turns out to have very good momentum resolution. It's a little confusing how to interpret that in terms of the strength of the excitation. But then we can also do this band mapping procedure, which takes, again, block states and band structure and maps them uniquely onto velocities. That has lower momentum resolution, but it allows us to characterize the strength of excitation quantitatively. And we're going to fill atoms in the first band of the honeycomb lattice. So if you will, there's fermions along all these points in quasi-momentum. The reason we use fermions for this is not just that they fill a lot of states in the lattice, but also that they're strictly non-interacting. So we can just understand things without interactions. And then we modulate the lattice at some frequency. So for example, if we modulate the lattice at this frequency, then atoms from the ground band can reach energies that are within this kind of orange shaded region. And so for this particular type of excitation, we would excite atoms only at a few places within the band from the ground state to the first band. To study the excitations from the first band to the third band, we use a wider range of frequency variations. We can also look at excitation from the first band to the fourth band. And then how do we figure out this response? We look at the distribution of atoms through either diffraction or band mapping images, and we compare with and without modulation and take the difference. And so you see there's a strong difference, and this strong difference tells me that at particular locations in quasi-momentum, we hit a resonance and we drove atoms from one band to another. All right, let me show you a panoply of such images. So these are data that are taken where we're looking at this range of shaking, this kind of orangish, dark orange range, brownish range. And so that's this range of frequencies from about 12 to 16 kilohertz. And we're looking at the response. In particular, we're going to focus on within the first Brillouin zone, how many atoms are missing or have been moved elsewhere because of this excitation. So let's look at these data. So at first, there's not much response. And then it looks like we're coming into resonance with a band, a first to fourth band transition that's at the M points of the Brillouin zone. That's cool. And then we keep going up, and now we see different momentum states are coming into resonance, like a crescent of these momentum states are coming into resonance. And then finally, at very high frequencies, stuff closer to the K point of the Kagome lattice comes into resonance. At every point in quasi-momentum, we can look at the spectrum, the excitation strength versus frequency, and determine the excitation energy. So if you will, this plot here is measuring the energy difference between the first and fourth bands of the honeycomb lattice. And more relevant to us here, this is the strength of the excitation. And you see, we see a pretty strong variation in the strength of the excitation across the Brillouin zone. And that tells us that the dot product of the interband Berry connection with a polarization vector that's at 45 degrees varies like this across the Brillouin zone. We measure that component. And now, through various shaking and spectroscopies, we can measure separately the X component and the Y component, its magnitude of this interband Berry connection. And from things like circular shaking and 45-degree shaking, we can also measure the ratio of these two quantities. So that's a lot of experimental data, or in other words, all these quantities influence the optical response of the material. So here's data that we've gathered on what is the interband Berry connection between the first and third band of the honeycomb lattice, or between the first and fourth band of the honeycomb lattice. And I'm comparing here the data versus what we would expect from theory, and the match is very pleasing. So really a lot of the features that we see in these theory plots, like these nodal lines, they show up in our data. These panels here, what we're doing is we're assessing whether or not this ratio is real or complex. Whether or not it's real, excuse me. And so here's the argument of that ratio. And the fact that that argument is typically either 0 or pi is confirming to us that the ratio is always a real number. That's neat. We have like this information on the interband Berry connection. But if you notice, I still don't know the direction in which the interband Berry connection points. There's an overall phase that I can't determine by taking a quantity squared. So if I measured, that the ratio between X and Y is 1, let's say, I don't know if the vector points 45 degrees in this direction or that direction. I can't figure that out. So now, in order to figure out, we have to pick a gauge. Let me tell you how we fix the gauge of our experiment. So as I said, we're always measuring this ratio. And for the data I showed you, we know the ratio is real. So the ratio is tangent of some angle, which is the direction of this vector in the XY plane. Now I have to make a gauge choice. And that gauge choice corresponds to picking a range for the arctan function. Over what range will I get an angle at the output? So I'm going to choose regions according to this color plot, which is inspired by what I know about the sign of the ratio between AX and AY. So let me take, first in this blue regions within the Brillouin zone, we basically observe experimentally that the ratio is positive. So let me fix that at this point. A positive tangent means a theta that points in the first quadrant of XY space. That's my gauge choice. All right, now let me look to the neighboring regions where theta flips sign from being positive to negative. And let me state that now XY. So sorry, the first should, which direction am I? Okay, right. So the first is in the first quadrant. Now tangent theta is going to be negative. So let me assign it a direction of the vector that points in the second quadrant. And I'll keep moving through all of the Brillouin zone and assigning like a direction in which the vector, Berry connection should point. And with that, I have the Berry connection, the interband Berry connection in a specific gauge. And here's the Berry connection as a function of that gauge, where I'm plotting in particular the angle theta in the XY plane. And regardless of what gauge choice I make, for this particular interband Berry connection, I will always see Dirac strings. There will be singularities in this definition of the interband Berry connection, which connects K points and K prime points. The K points and K prime points act like magnetic monopoles in this space, and they're connected by Dirac strings. You can see that we have these Dirac strings. So if I look around the gamma point, let me just go around a circle around the gamma point. I don't expect any Dirac string to hit the gamma point because there's no singularity there. Then here I have an angle theta that varies smoothly around the entire circle. In fact, we see that it winds around twice, which is an interesting geometric feature. Similarly, around the M points at the edge here, I can go around in a circle and I just see a straightforward variation of theta. It winds around once. So that's the kind of nature of the Berry connection at the M points. But at the K and K prime points, when I go around in a circle, I will inevitably face these jumps of pi. And that's where, as I go around as I go around the circle, if I go all the way around the circle, making always a consistent choice of the interband Berry connection, I will necessarily end up with a glitch. And the locus of that glitch is the Dirac string. So between the first and third bands of the honeycomb lattice, there is a Dirac string in the interband Berry connection. It has to do with there being Dirac points at the bottom band, but not the top band. Between the first and fourth band of the Berry of the honeycomb lattice, that Berry connection does not have Dirac strings, and indeed they don't show up in our gauge choice. Wow, that took a long time to describe. It's the first time I'm presenting this stuff. Okay, so where we're going next is we'd like to take these ultracold fermions and place them in flat bands, and we haven't done so, so I don't have a lot to say about it. Once the Fermi energy of an interacting Fermi gas is placed in a non-dispersing band, then you get to write lots of papers because things get super interesting. For example, the most straightforward observation is that there's no longer a Fermi surface. There's nothing that distinguishes filled states from empty states, and therefore any piece of condensed matter physics that starts from a Fermi surface is not valid. That includes the theory of superconductivity, that includes the theory of metals. So that'll be interesting. All right, that gives me a little bit of time to tell you about the second project that I wanted to talk about, so I'm going to have to go a little bit quickly. And that has to do with our experiments on ultracold titanium. So it turns out that people have made quantum degenerate gases of quite a few elements at this point. And having all these elements accessible has fueled a lot of progress in ultracold atomic physics and kept us busy, has allowed us to come tell interesting stories whenever we're invited to a seminar. But even with all these elements in the periodic table, you might wish for more. And the thing we were wishing for in particular was to be able to create topological superconductors in a quantum gas. So I won't describe what topological superconductors are. They have Majorana edge modes, and they might be the thing of a quantum computer. I'll just say that much. But what produces them is a combination of features, which is superconductivity and spin-orbit coupling. And those things together can sometimes make a superfluid adopt a topological phase that is interesting. So it turns out that we can derive all of these ingredients in a cold atom experiment as well, because we can work with fermionic atoms. We can have interactions that allow for Cooper pairing. We can create spin-orbit coupling. Spin-orbit coupling is done by driving a Raman transition on atoms with light that is not collinear, which changes both the spin and by recoil, the momentum or the orbital motion of the atoms. And then we also need atoms where we can mix various spin states together and have them be long-lived. So as I understood, but maybe I didn't understand fully, that kind of required a little bit more searching through the periodic table. And in particular, we need fermions. It turns out that of all the atoms that have been laser cooled and brought to quantum degeneracy, there's not many fermions. Fermions are kind of a rare breed in the periodic table. Most of the work in ultracold Fermi gases has been done with just these two isotopes. A little bit more work is coming in with the lanthanides. But certainly we'd like to enrich the family of fermions because there's very few of them. So we thought about it. We realized that maybe unbeknownst to us, a lot of transition metals can also be laser cooled, at least as the first stage toward bringing them to the ultracold regime. And moreover, a lot of these transition metals have fermionic isotopes. So if we can bring these atoms to the quantum degenerate regime, we can really grow the family of ultracold fermions by quite a bit. So anyhow, so this made us want to work with one of these elements. In particular, we started experiments with ultracold titanium, or with titanium, try to bring it to the ultracold regime. Here's the electronic structure of titanium. These are even states in black and odd states in red, sorted by energy and by their total angular momentum. It turns out that laser cooling titanium atoms out of the ground state directly is not doable, as far as I know. Rather, laser cooling would work if we can place atoms in a metastable state. And then it turns out that this metastable state actually supports two different transitions, both of which look to be essentially cycling transitions, which should support laser cooling. One of them is broad. It's about 10 megahertz wide. It's essentially the same as a D2 transition in an alkali metal. And the other one is narrow, about 10 kilohertz wide, and is at this different wavelength. So we set about to try to make this work. So we first had to learn how to get atoms out of the ground states into the metastable state. And then we had to get atoms we had to drive this laser cooling transition. To get the atoms out of the ground state, we chose to do some optical pumping. So we found a transition at this wavelength where this fine structure state, in particular of the ground state, will populate the metastable state with roughly 50% probability. And so we set up an experiment. We tried a lot of things, but eventually we set up this experiment where we generate a beam of atomic titanium, actually by turning on a titanium sublimation pump. We turn on a TI-sub pump, it spits out titanium. The titanium atoms pass through a region of optical pumping and then go directly into a MOT. So this is almost like a vapor cell magneto-optical trap. We just try to trap the low energy atoms that are coming off of a high temperature source. And it turns out to work. So this was our first result from about a year ago. So we learned how to make magneto-optical traps, at least, of titanium. These first experiments were done with the 3 bosonic isotopes of titanium, 46, 48, and 50, all of which have 0 nuclear spin. And these were simple to work with at first because the 0 nuclear spin means there's no hyperfine structure. The spectrum is very, very simple. And that was, anyhow, it was kind of a fun result for us. But of course, one of our big motivations was to work with ultracold fermions. So we have to learn how to cool the other remaining isotopes, which have a non-zero nuclear spin. And the first challenge you face then is that you don't know the hyperfine structure. So all the states that are relevant to our laser cooling transition, the ground and excited states of the optical pumping transition, and the ground and excited states of the laser cooling transition, are all bestowed with hyperfine structure. And a priori, we didn't know much about this hyperfine structure. There were reports of the hyperfine structure in the low energy states, but not in the high energy states. So this was a pretty fun campaign, like actual AMO physics, which is a rarity for me. And we had good support for a bunch of quantum baloney. And yeah, so we worked a lot with theorists who actually can calculate the hyperfine structure and can compare to our data. I won't talk about this at all, but we make measurements of the hyperfine structure in a sort of a 2-color beam experiment, and we're able to fill out now for the first time experimentally the A and B coefficients for some of these levels. Anyhow, with this information, we now know what the hyperfine structure is, and so we can try to laser cool the fermions as well. So we choose to optically pump just one of the hyperfine levels, so that's going to give us reduced efficiency in producing an atomic beam of metastable titanium, but so be it. And then we're going to drive not just the laser cooling transition, so the F to F+1 transition, but we're also going to drive 2 repump transitions to keep atoms in the stretched hyperfine state where they will stay engaged in the laser cooling transition. And by providing these 2 repump tones, we believe an atom should scatter at least something like 500,000 photons before it goes to these other hyperfine levels where we would lose track of it. Anyhow, short story is that it works. We're able to make magneto-optical traps of both isotopes of fermionic titanium now. The fermionic MOTS are a little bit different than the bosonic atom MOTS. One thing is clear that for the fermions, if you want to keep your atoms in the magneto-optical trap for a long time, you need these repump tones. If you turn off the repump tone, then the lifetime becomes quite a lot shorter. Another thing we confirm is that the fermionic atom magneto-optical trap is darker than the bosonic one, because the atom can sort of hide in these other hyperfine states for a while. That actually is good for loading large numbers of atoms into a MOT, so that's going to be good for us, and so forth. So we have good information on the fermionic MOTs. The last achievement of late in the lab is to realize narrow line cooling on titanium. So titanium also supports a narrow laser cooling transition from this level to that level. We think it's about 10 kilohertz wide. We found it. We didn't really know where it was, but we found it experimentally. And we've learned how to laser cool atoms on this particular transition. And I really appreciate the fact that people had worked with other elements like erbium and dysprosium beforehand, because all we needed to do was read their papers carefully, and then we could finally understand what we're supposed to do. So for example, one of the things you learn from those papers is that you should actually, you run your magneto-optical trap with blue detuned light instead of red detuned light. That was a surprise to me. But it turns out that this blue detuned light, if you send light onto the atoms that's blue detuned, you actually optically pump the atoms into a state that is magnetically trapped inside the spherical quadrupole field. You can see we get a lot more atoms if we shine blue detuned light on our atoms than if we shine red detuned light on our atoms. So that's one thing. And then the second thing you realize is that you don't need 6 beams for a narrow line MOT. You just need 1. And in fact, you can shine that beam in from above. So it's pushing the atoms down, and that makes a magneto-optical trap. And I think of it a little bit like flypaper. So when we turn on this blue detuned light, we optically pump atoms into the magnetic trap, but formed by the spherical quadrupole field. But we also are exposing the atoms to blue detuned light, so we're constantly heating them up. So the atoms kind of fly within this, almost like a bunch of flies. They're flying all over the place inside the magnetic trap until they find this location where the narrow line MOT, the narrow line light, actually comes into resonance. In fact, they sit a little bit below it, where where that light is red detuned from their resonance, and they get trapped there. It's like the flies all get stuck on this flypaper down at the bottom of the MOT, and there's a magneto-optical trap on the narrow line. See, it's a line, and it's below where the atoms were trapped magnetically. And these atoms are fairly cold, so we measure a temperature a little bit below 2 microkelvin for these atoms. So that's the progress of titanium, at least. We have some big plans for what to do with titanium. We're interested in using titanium for a telecom band optical clock. We have ideas for how titanium atoms can be placed in optical tweezers, so we can do all this quantum mumbo jumbo. We want to work with quantum gases of titanium, sort of large quantum gases. We're building up an apparatus that'll help us do that. We might be tempted to go laser cool some of these other transition metals also, or maybe we'll just stick with titanium. Okay, so that's all I wanted to tell you. So this is work that comes out of the E9 team, which is my atoms and optical lattice experiment, and the E8 team, which has been working on laser cooling of titanium. I mentioned our theory collaborators in Delaware that have been really helpful for our understanding anything about titanium. I did not talk about the experiments that happened on our atoms in an optical cavity experiment. I've talked about this previously. So just as a reminder, we have an experiment where we can create a one-dimensional tweezer array of atoms inside of a strongly coupled optical cavity. And just since the crazy cavity workshop, we have a little bit of updates. We see a spins version of the Dickey model. We've characterized the phase diagram that includes both U1 and Z2 symmetry breaking phases. We find that the collective spin of the atoms emerges from the experiment itself. You can even have a completely unpolarized gas to the start, but eventually the atoms will polarize themselves into these phases. And that partly explains why they're so incredibly long-lived. We have atoms that sit in this phase and keep scattering light for like a second. It's a little crazy. We've made a lot of progress on mid-circuit measurements where we can hide atoms optically so as to measure other atoms selectively. And we now know that that preserves the coherence during the measurement. And then most recently, we've been seeing finally Rabi oscillations on Rydberg transitions where the atoms are placed inside of the optical cavity. So that's good news. It means that we have control over the electric fields under that situation. But that's a lot of information. Thanks for your attention.
Do you have questions?
I have sort of a dumb technical question.
I wouldn't expect otherwise.
You know, I guess you replay stuff. So your titanium comes from a tricep.
Yeah.
Then you're going to try to generate some other. So how does look? Where does that?
Right, right. So where are we going to find like the zirconium sublimation pump or the ruthenium sublimation pump? I think zirconium sublimation pumps actually might exist. I've read papers on that, but not ruthenium. Ruthenium is really, really hard to, it's very refractory. For that, I would probably turn to other experiments that we did where we've learned how to laser ablate metals into room temperature buffer gases. And then you poke a hole in a cell and the laser ablated atoms come along with the buffer gas into a vacuum cell. And one of the really neat things we saw in that means of generating a beam is that you directly populate the metastable state that you need for laser cooling because the ablation process is so hot. And the collisions with the buffer gas don't relax the atoms, is what we've observed. So in titanium, I think our TiSub plus optical pumping turns out to be a superior source and is certainly more convenient. But for all the other ones, I think we could rely on ablations. You could ablate ruthenium or zirconium or whatever. There are some other ones that are actually less refractory, like iron. You can produce a beam of iron with less of a headache than creating a beam of titanium. So not all of them are hard. Titanium turned out to be kind of a hard example. Yeah.
Thanks for a great talk. I just wanted to ask a bit about the prospects of the fermions and flat bands. I know it was about the challenge that goes on in being excited for trying to get it to be excited. So the idea, all of that goes away for fermions.
That's the idea. That's exactly the idea.
Are there any wrinkles or caveats there, or just
Yeah, good question. So the wrinkle would be, that's our idea for going to the fermions, is now we should be able to look at a equilibrium situation where the flat band is the relevant physics. That's why we switched to the fermions. I became convinced that the bosons are never going to give us the flat band physics that we're looking for. The fermions might. So in the kagome lattice, there's 3 s orbital bands and the top one is flat. I think that's a great candidate for us to study. There's no large band gap to overcome. We just kind of keep continually filling fermions, and then the highest energy fermions will sit within that flat band. The honeycomb lattice, if it's deep enough, has flat bands in the p orbitals also. So you could work in the honeycomb lattice, but there, first of all, you have to overcome this big gap. And then secondly, now you end up with systems where you have actually 3 fermions in a site, down, up, and then 1 more. And then you allow 3 body losses to come into play. So I think the physics in the kagome lattice will be a little easier to access. Will we be able to access it is a fine question. So the flat band is flat. It has really no energy variation. So if you now think about filling atoms within a lattice, but where there's some kind of background potential, then maybe at the center of the potential, the chemical potential is above the flat band. And at the edges, it's below the flat band, and the transition is instantaneous. So in like a 2-dimensional system, you might expect there's like a line along which the chemical potential lies in the flat band, but it doesn't have any volume. So I'm a little worried about that. We're building in a means to like flatten down the background potential with some blue detuned light, so that'll help a little bit. And then from there on, I'm hoping that interactions will kind of broaden the compressibility of the flat band, and that'll allow the atoms to fill a larger region.
So I see you have these papers about the titanium boxer.
Yeah.
Is there a possibility of using upper level, longer wavelength?
I haven't looked. They're probably right. So, John's referring to this idea that, well, a lot of us are interested in like collective atom-light interactions, and we'd like to build. Oh, sorry, Emily, and because of that, a lot of us, because we're interested in what she's interested in, are interested in collective light-atom interactions, and these collective light atom interactions, at least in free space, become a really big deal if the atoms are within an optical wavelength or much closer than an optical wavelength. But if you're using optical structures to trap the atoms to begin with, it's hard to get them that much closer. So people are looking at atoms where you could maybe trap an atom with some very short wavelength light, but then look at collective emission of long wavelength light. That's what John's referring to. That's a long way of saying I don't know. There's a lot going on in titanium. I'm sure there's also long wavelength transitions, maybe not in titanium, but maybe in some of the other in the other atoms. And in a complicated atom, roughly any transition is allowed. So if you do find an even and odd state, there's probably a transition that's not so weak between them. And then you could look at this collective physics. And even if it's not a closed transition, I don't think that that's going to be a showstopper in terms of getting to some of the interesting collective effects. So. Thanks.